Man in Madison beat you to class today. Big deal. This morning you were like, I'm leaving extra early. I'm just gonna show where you. I'm gonna show that I made it. Good. Okay, so we're talking deflections. So a little side note. So we got deflections today, maybe spilling over into Wednesday a little bit. Friday we have a guest speaker. There's a guy he's a former student of ours, Kinsey Skillen. He just got his PhD maybe 3 or 4 years ago from Purdue. And then he's gonna be in town for some other event, and he wanted to talk to our grad students. And so usually, in the past we've had this grad seminar. It's being rebirthed as we speak. But right now we have all the grad students in one spot. So I said, why don't you come in and just give us a talk? And so he's currently a professor at Texas A&M. I have no idea what he's going to talk about. He's like, I could teach one of your classes. I was like, I don't know, just talk about something you want to talk about. So he's going to come back. He's going to come in and talk about research and stuff like that he's done, and maybe potential opportunities for you at Texas A&M and stuff like that. So Kinsey, that's this Friday. So by the end of this week we'll be done with deflections. Maybe started prestress losses and how to calculate prestress losses, because that's going to go into our calculations. Then next week we'll finish up prestress losses, begin and maybe complete composite construction, because one thing, a very common way that we construct these, you have pre-stressed members, and then you put a cast-in-place concrete deck on top of it. It's a very standard way that we design bridges and stuff, and even some building elements. And so you have 2 different strengths of concrete, and one's pre-stressed and one's not, and so one has pre-compression, and then the top slab that has no pre-compression, and how do you go about designing for those things and all the different load. If you thought there was a lot of things to manage in terms of load cases before you added on a composite slab, you're in for a treat. There's like 10 more things we have to check once you add that composite slab on top. So then we'll kind of, maybe the end of next week, beginning of the following week, we'll be done with pre-stress. So we have a couple more homeworks. We have a deflection homework, a pre-stress loss homework, and a composite construction homework. And then it's a little, which I owe you homeworks, by the way. That's this week. I'm going to promise you at least one of those graded this week, possibly 2. It's a promise. If I don't, we should put in a if I don't thing. What if I don't? What's that? Deal. Who said that? Brandon? Yeah, if I don't get you at least one homework this week, I'll drop your worst homework grade. That's an easy one. I can do one, right? I can do that really easy. I won't break that promise.
You're like, I was going to do that anyways.
What's that?
You're like, I was going to do that.
I was going to do that anyways.
Well, it turns out you're locked out of your office and you like flood.
Yeah. Let's see. I gotta think of another 2. If I don't get 2 done, what would be?
Extra credit on the midterm.
Well, I'll give you extra credit on the midterm. If I don't get 2 done, I'll give you extra credit on the midterm. These are promises.
What is the
Empty promises. What's that?
plan there with the exam?
So then that's what we're going to talk about a little. So we're kind of almost done. So maybe 2 weeks out we'll be done with pre-stress stuff, and I'm done with homework. And by the way, that's the last homework. We're not gonna, the rest of the class is kind of survey of the class. So which then you guys turn off your brains and stop listening. But at some point, so we have bridges left, right? And bridges is going to be just like a survey class. So again, our goal is to be, which code to grab when somebody tells you to design a bridge, and then what sections apply to you. So I think it's informative in that sense. And so we'll have a couple of weeks to go into that bridge code, and then we're going to have Kyle Boyd come in and teach us post-tension concrete design and like the fundamentals of that. You won't, will you be able to be a beautiful post-tension floors? No, but you at least understand the steps involved to do it. And coming from somebody that does it all the time, which is something I cannot offer in any way. And so that's a good little section. So that's kind of in there. When the exam takes place, last time I taught this class in 2019, it was, we took the exam on Halloween.
I think that's what it is.
That's like
Yeah. And you got extra credit if you dressed up. And if you dressed up for the exam. And in fact, I don't think anybody, I think maybe one person dressed up for it. That's all they took advantage of. The year before, or the 2 years before that, man, it actually might have been even further, 8 years ago or so, they dressed up as me. The whole class dressed up as me. Yeah, the girls painted beards on and stuff. Yeah, I thought that was good. Anyways, so that probably around that timeline.
And it's gonna be on all the pre-stress?
All pre-stress stuff.
Wow.
Yep, all pre-stress stuff. And then we'll have one more exam. And so like Kyle's lectures will be in there someplace. And then you'll have one more exam. It'll just be like fundamentals of bridge, just conceptual fundamentals of bridge stuff. Yep. Anyway, that's kind of where we're headed. Any questions about what we have left? Yes, Dawson.
Are our exams in class, or are they?
Yeah, they have to be. I think this is a big thing, and Dawson's aware of this. They passed a new rule that you cannot do evening exams anymore. And so, like if you think back when when I did dynamics, we would have common hour exams in the evenings for 2 hours, and they from high above it's come down that we cannot do that anymore. So it has to be during class time. That being said, I mean, does anybody have class right after this? I mean, I do. I have class right now. I have class right now. I mean, I'd like to give you a couple of hours to do it. I mean, in the design courses, nobody said you couldn't do it for grad classes. So I'm going to take that as we could still have a little bit of flexibility there. I just prefer, I don't like the 1 hour. I don't like the 50-minute thing. It's rushed, it's intense, especially for a design-oriented course like this, I don't like it. Yeah.
Damon just did steal his take home.
He did his take home. I don't like those things. I don't trust you sons of bitches. I wouldn't trust you to do that.
Is that thing about no evening exams, is that for the whole campus or just?
All campus.
That's pro.
No, it's some people are working and more people it's becoming more difficult for them to come to school and do the evening exams. They can't find daycare. They're all in this, and I'm just like, this is bullshit. It's hard for everybody to do this stuff. Just freaking suck it up. Like, what are you gonna do when you go to work? Like, we need you to work late tonight. I'm sorry, that's not gonna work with me because I've got plans tonight, or I can't get daycare tonight, or and there's the deal. If there's really truly a problem, if there ever has been a problem, we've accommodated them. We absolutely have never stuck it to somebody if they couldn't make an evening exam, right? We just say, sure, yeah, we'll do it at a different time. I just gave 2 makeups right now. Like, it's just. We absolutely do that all the time, but for some reason, Cruzado herself has had absolute. And then a couple weeks ago, we got an email from our dean saying it's okay as long as you provide like accommodations. And then we got this hell no coming from the provost saying no, don't do it. So I don't know. I think it's bullshit. I don't like it. If you don't like it, you should complain. Not to me, to the other people up above me. Yeah. Somebody had a question. I don't know. So the answer is I don't know. I don't know. I'll have to look to see what it does. We could do a conceptual 50-minute. I'm not sure. I don't remember how it does. It's kind of hard to do this stuff in person, even in 2 hours trying to do some of this design. So it'll probably be conceptual, and we might be able to do it 50 minutes or a little bit more. Or we could come. Oh, I could do early.
Yeah. Do like 9. Unless that.
According to Craig Matson, the geotech guy, when we did his exams from 7 to 9 in the morning, and they said you couldn't do that.
But we're gonna be secretive. We're gonna have a secret society, and we're gonna allow.
There's a class in here for this stuff.
All right, we'll find a spot.
But I'm not down with it.
Yeah, we'll do it secretively, and then if we get in trouble, then I'm gonna find who did it. I'm gonna fail you. I don't know. We'll see what we're gonna do. We'll come up with something that works. Okay, so we're right in the middle of talking about calculated deflection. As an academic, I really enjoy calculated deflections of pre-stress of just members in general. Like it's at one time we get to flex our mechanics skills a little bit, right? I mean, it's gonna end up being we're gonna look it up in a table, but just like before then, let's stick with it. Like just this mechanics. Let's go back to your sophomore level of mechanics and materials. to kind of see where these things came from. And so we're kind of doing it. And it's good to understand all that too. So when you get into these other methods, you kind of like, oh, I see what they're trying to do. But so we talked about this, kind of the basis here, the material level, right? The stress strain response, right? Depending on how the material behaves, we can calculate the section level, and that's called the moment curvature relationship. You'll see that all through your careers. You'll hear people talking about it. It's just if you have a section and you apply moment, how much curvature does it give you, right? The moment will like vary along the length of the beam, and so how much curvature you get varies as a function of x. And so like the overall response of this is going to be an accumulation of a bunch of different section level analyses as you go along, right? So it's going to start like, if I was trying to get the full force deflection response of a member that looks like this, I'd say what kind of moment does this give me? I come over to my moment curvature relationship, I look up, given a moment, what kind of curvature I get, and then I integrate that as I go along and just kind of keep doing that cumulatively along the length. This moment relationship for this member is going to be different than this moment relationship for this, which means when you go to the section level, and then the sections are calling on our stress strain response to see if the material is yielded or not yielded. That kind of governs where this comes from. And so all this stuff is kind of at play as you're going along, especially when you go into nonlinear, okay? When we do elastic deformation stuff, things get really easy because our stress strain response between our relationship between our stress and our strain is just E times epsilon is equal to sigma. And then our moment curvature relationship, we're in the linear range. That moment is related to curvature with just EI, right? And then when that happens, going to the member level is a little bit easier, okay? And so that's what we talked about briefly is like, how do we calculate deflections? Well, like I said, you can look up what your moment is, read off what your curvature is, and then integrate those curvatures along the length, and that'll give you what your deflection is as a function of x. That's one way of doing it, okay? And that works for nonlinear behavior, but let's simplify it down for linear behavior. Because you might be called upon to do a nonlinear analysis at some point. Yeah, maybe in your life. Depends on what you're doing and where you're working. So let's talk about the elastic. This is mainly where you're going to live in terms of calculating deflections. When we have elastic deflections, this curvature, right? U double dot is equal to the curvature. It's just equal to m over EI. M is a function of x. Right, and that's just, we saw that up above. That's just coming from what that slope is right there. Right, m over EI, that's the slope of that curvature. Okay, and so you can write this a little bit different. You say EI U prime prime is equal to m as a function of x. And this is kind of lead into something that you've seen before. And then we'll also add in, if you take the derivative of the moment, dm dx is equal to v of x. And this comes from equilibrium. You could look like Vx times dx. If you like, and this is where you can look back in your mechanics materials book. You'll see like Vx times dx equals dm, the difference in the moment on either end of the little block thing. You can look back at that, but that just goes to equilibrium right there. So that just means if I take the derivative of the moment, it gives me Vx. Well, my moment's equal to EI u prime prime. So you get this EI u prime 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 is equal to V of x. And then another equilibrium relationship is dV dx. Dx is equal to negative W of x. And both of these are equilibrium relationships. And then you apply that here, and that's where you get what we're after here, which is EI u prime 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 is equal to negative W. Everybody remember that thing? That's my favorite way to do deflection problems, is that equation. Of course it covers as mechanics and materials, correct? There.
Yeah.
Yeah, use that one. That one's great. That one applies to everything, and then this is actually the fundamentals behind like finite element analysis too for beam elements. It's all tied into this equation. You set different boundary conditions and solve, right? So you have a fourth order differential equation, so you have to set 4 different boundary conditions, and it'll be like the deflections and rotations at one end, and then the moments and shears at the other end, and you kind of set those things and you solve, and it gives you u as a function of x. I think it's a very robust way of solving it. You could solve you cannot do nonlinear, but you could solve indeterminate structures and all that stuff with this equation. And again, it's the fundamentals for like beam elements and finite elements. This is kind of cool. Anyways, if you look back at it, it's just like, I did this a few years ago when I started teaching. It's like, oh yeah, where the hell did that come from? And you're just like, oh yeah, look at that. You integrate the curvatures, it's just m over ei, that's that relationship, and you add in this equilibrium, and then boom, you end up with this fourth order differential equation. And it solves everything. It takes into consideration the constitutive relationship, right? M over ei is the constitutive relationship. It has equilibrium, and then it has compatibility in there as well. So it has all those 3 components. You can solve all statically indeterminate problems. Anyways, there's that. Okay. So then that's just kind of the fundamental, how do we calculate elastic deflections in any kind of member, okay? So now, how do we calculate these things in elastic, uncracked, pre-stressed members, okay? So there's deflections from external loads. So the way we're gonna do it is treat these things as internal and external loads. So we calculate the deflections from internal loads. External loads, and then we have to get a little tricky when we do the internal loads. So deflections from internal loads, there's a couple ways you could do it. You could solve EI U prime is equal to negative W x. That's how I would do it, because I like to do fourth order differential equations, but you would look at what your external load is, and you apply the load, and you find point loads, and you do all that stuff as well. Or you could do tables. This would probably be how you're gonna do it. That's fine, totally fine. If you're not as smart as me, you look up at the tables. No comment. Just kind of joking, but then also 100% serious. I'm a doctor. I'm way smarter than you guys. That's not true. That's the easiest one, right? Everybody's got the steel manual, right? You open up the steel manual under the beam tab. You look under the beam tab, and then you play a matching game, right? You're like, okay, what does that match this? Like the problem I'm trying to solve, does it match this? And then you look up that. So an example is like you'd end up with 5WL to the fourth divided by 384 EI, right? You would just look that up. That's for a simply supported beam with a uniformly distributed load with simple supports on both sides, right? But you'd look it up and just play a matching game for that. And that's totally acceptable in this class. Okay, and the other way that you could do it is FEA or a structural analysis program. Okay, something like that, you can calculate your deflections. In the real world, what do you do? In the real world, if you have to check some deflections, you use your steel manual, look at those tabs, you just have them memorized, or what do you do?
Yeah, it's simple.
What's that?
If it's simple.
Simple one, yeah. Or if it's a little more complicated, I can see just lining it up in a structural analysis program of some sort and say, what are my deflections? Yeah, right. Because you could do element by element. You don't have to have like a whole finite element. You could just do like little elements at a time, right?
Well, in RAM, we put the whole steel model together.
Okay. And then it goes and just does it all. Yeah. Click of a button. All the stuff you learn in structural engineering is just a click of a button when you get into the real world. I mean, kind of some of it. But you need the fundamentals to understand how it's working, so you apply it right and you don't get crazy. I mean, I was once talking to a practicing structural engineer, and he was talking about, I asked him, like, how do you calculate your deflections, your pre-stressed members? And he's like, well, I just hit, I go in and I hit the cracked section analysis button on the FEA. I was like, what is it, like, so what methods is it using for that? He's like, oh, I don't know. It's just doing it. Oh, no, that's not right, man. You should know why you're clicking that button, right? Like, you should know that. In his case, the more I read into it, the more I talked to him, I realized that what he was clicking had nothing to do with it had nothing to do with like the deflections. It had to do with some other analysis that he was doing. And I was just like, dude. I gave him an F. I just wrote an F on the thing. Sorry, it doesn't work. He wasn't a student of mine, so that made it awkward. But anyways, okay, so that's it. I mean, that's how we're going to do it, right? Is you're going to look it up in the ASC table. That's perfect. That's great. That's easy to do. Calculate. That's from the external loads. So what do we do when you have the pre-stressing? Because your table doesn't necessarily have pre-stress deflections. Right? I mean, it won't have that. It won't have internal forces and internal moments due to the pre-stressing. Like that's different. One way to do it would be that equivalent force method. I mean, this is kind of an equivalent force method. And I'd say this is part of it. So we're going to find out an equivalent force that does the same thing. Okay, and again, you know, this is going to be used when Kyle talks to us about post-tension floor design. It's all equivalent force method. You say, all right, you turn all of your internal stresses into internal forces, and then into external forces. You turn your internal stuff into external forces, and then you apply it to your structure and calculate. That's kind of what we do here. We say what gives us the same moments and shears that this thing does. So let's equivalent force method. Let me go here. No, it would be the one. We'll watch it play out here. Yep, equivalent force method. That's right. You find the loads that give you the same effect. You find the same external loads that give you the same effect as the internal loads, and then you apply the external loads to it, and then calculate deflections or moments and stuff like that to it. Even though you're treating it as if. Watch this. Equivalent force method. We'll say this first. Turn internal loads into external loads and use tables or calculate deflections. Okay. Drawing here. So in this particular case, so this would be a member with a pre-stressing strand, one depressed point. Right, so that what I've drawn right there is just the CGC. Right, so on the ends, right, so we're going to try to calculate the deflections of this beam due to these internal loads. Okay, and so this thing has 0 eccentricity on the ends, a max eccentricity in the middle, and then back to 0 on that side. So that's the pre-stressing strand. Blue is the pre-stressing strand. Okay, and so the moments that this thing would cause negative moments because it's going to be causing compression at the bottom and tension at the top. It would start out at 0. It would go to an ultimate value like this. Right? This is what those moments would be. That's the moment diagram for that. Right? And then this maximum would be negative FP EP max. That maximum moment from there would be FP times EP max. EP max would be that total distance. I guess it would be this right here if you want to. That'd be EP max. All right, so FP times EP max would give us that moment. And it's negative because, again, that's causing a pop-up. And then it zeros, right, at the moment diagram, it zeros out at the end because it goes right to that CGC. So there is no internal moment on the ends. It works its way up to a maximum in the middle with FP and EP max. Okay? And so what we do is we say, okay, what loading would cause that same moment diagram? Like what kind of external loads would cause that same moment diagram?
Point load?
Yeah, point load. Yeah, point load in the middle. Which way? Up. Yeah, so a point load in the middle would cause this exact same moment diagram. So if I put a point load right here, my moment diagram would be exactly the same. And then this is what I mean by the equivalent loads, right? We're going to call that Q. And point load up like that would cause the exact same moment diagram. Right. And then this one, the magnitude of this moment would just be QL over 4. Right. PL over 4 is the moment at the center of a simply supported beam with a point load. Okay? And so we equate those things to each other, right? So the equivalent load would be like QL over 4 is equal to FP EP max. Yo.
I have a question.
No questions allowed.
Do we need to make that FP horizontal so that it can be perpendicular to that EP? Because FP, it's kind of slanted.
Yeah, good question, and that's been there all along, and we've ignored it, and we're gonna keep ignoring it. Okay, and that's a great question. That's a great question, Daniel. Is in technically right? He's absolutely right. Like in all of our equations, the fundamentals, and we should have said it back at the when we first introduced these mechanics, is that FP we assume is going like this. Right? We assume that it's acting like only horizontally, right? But really it has a vertical component to it because it's slanted down a little bit. We ignore that vertical component. We just pretend it's always horizontal, no matter what. And so that's fundamental. If you look back to all of our equations previously, like our big our big FP EP over AC, or FP over AC minus that was there too, right? Even then, we were assuming that it was only acting this way, but really there's a vertical component. The only time we ever consider the vertical component to it, and this is what I mean with this, right? Like, right? There's a component like this and a vertical component like that, right? You could break it into that. The only time we consider that is in shear design. In shear design, there's one of the variables and one of the methods, and you'll see it, that gives you a little bit of a boost to account for the fact that the FP has actually got a little vertical component. The other thing to keep in mind, these are always very exaggerated, right? These are very exaggerated. Usually it's like 10 inches of a drop over 60 feet of span or something like, right? And so is it okay to have this? Yes, because it's usually that vertical component is very small compared to, how long. And these are never drawn to scale. Like if we drew that to scale, it'd be like this would be way longer, and you'd barely even see the depress in it. So, yeah, good question though. Absolutely great question. I think one of the statements we say at the end, we have like one summary thing of things that we didn't account for that maybe weren't completely correct, and that's one of the things we bring up. Yes.
Is that negative FPE?
Yeah, so they're both negative.
The revolution.
I called it. Yeah, so I'll call it negative here. I'll do like that. If you put a negative over there, so they're both negative, and so I cancel the negative there. Good question. Okay, so then you could solve for what that equivalent force would be. That equivalent force Q is equal to FP EP max times 4 divided by L. So then you would come into this thing and say, all right, my equivalent force is FP EP max times 4 over L. I have now an equivalent force. And then at this point, I can calculate the deflections. This guy right here, you could find in the tables, the AISC design tables, that this is, wait, does anybody have that in their head? What the deflection is of a, come on, what's that? to a point load. In practicing people, you got that in there? Matthew, you don't have that one memorized?
I just looked it up.
What is it?
Px over 48 di times 3L squared minus 4x squared.
That's along the whole length. Yep. The maximum deflection is PL cubed over 40 ADI. You get the practicing people, get this in there. Get that in there. Get that in there, Matthew. Huh? But you knew where to look it up right away. Did you look it up in the AIC design, or what did you?
Just Google.
Googled it. That also works as well, right? Any way you want to get it. But so the deflection's at the center of a simply supported beam due to a point load. The maximum deflection is PL cubed over 40 ADI. So then you would go to that, and you'd look it up, you'd say, all right, deflections equal QL cubed over 48 EI. Right? And then instead of putting Q there, just leaving it as Q, you put this Q in there. And so then that FP EP max times L squared all over 12 DI. So that is what that deflection would be from that. It's pretty clever. Right, I just kind of added it and then simplified it. I guess we could just draw that. Right, that's what you end up with. So that is what your deflection is due to a depressed point like that. Okay. If it didn't have the CGC, if it didn't go to the CGC, right, and there was moment left at the end, it would be kind of offset and this. And so you'd have to look up, well, what kind of loading condition would give a offset and that. And there'd be a constant moment on either end, which you can look it up in a table. That deflection from that one plus this load from the Q. So you do like a combo of the stuff. You say, okay, what combos of loads give me those deflections, right? And then you can, it's all in the elastic range. You can all do superposition in there. Does that make sense? If you would have had, like if this thing, well, it's not gonna work with that thing. If my depressed points were like that, then my moment diagram, I would have moments at the end. This thing would be shifted up a little bit. And so you'd have to look at the combo of loads that would give you the same moment diagram. And the combo of loads would be a constant, which would shift it, and then the point load, which would give you the V shape to it. Okay, so then the other thing that you could do, so that I think is like the most robust way. The other thing that can be done, and this is what Stanton does in his notes. He kind of developed this. I don't know if he developed it or if he got it out of a textbook or where he got it, but he's like, you can use this table as well. So you say, or use this table. And we'll show you how to use that in a second. I use this table from Stanton's notes. Okay, and it just says, like if you have pre-stressing that looks like this, where you just have, I've never seen one of these, but you just have no depression point on one side and then a depression point on the other side, with the epsilon to P2, it's going to be 1/2 delta 2. You calculate delta 2 down here, and then your deflection is just 1/2 delta 2. If you have a case where you have 2 depressed points, you can calculate that displacement is 1 minus 4/3 alpha times delta 1, and then what alpha is that distance right there, how far out that, what fraction of your overall length your depressed point is at, and then delta 1 is right here. You calculate delta 1 and then plug it in. So this is kind of like, again, kind of a matching game to combine these things. So you get to play with this at some point when we calculate deflections of a beam, okay? Just to kind of close it out, as an example, this is what we did in the example right here, right?
Does that assume all those go to the CGC?
Well, no, see, like, yeah, this is what I said before, because this one is a constant across it, right? And then this one is epsilon's a P1. So if you wanted the case where it was like offset, like I had in the previous one, you calculate these deflections and these deflections and add them together. You do both. Does that make sense?
Yeah.
Yep. And I think he does a couple examples in his notes, so you can kind of work it. So again, if these ones, this assumes CGC, this assumes CGC, this assumes CGC. If it doesn't go to CGC, you add in one of those guys to kind of shift it up or down, depending on how far off the CGC it is.
Sorry, can you say one more time what type of loading will shift you up? For if you were gonna do the
Yeah.
equivalent force.
Yeah. Back to the equivalent force. So no, you're okay.
I thought you said distributable, but I don't.
No. Just a constant moment is what I was saying. So like a constant moment, right? If you had a constant moment, you have a constant moment diagram. So if I went like that, it would just be my moment diagram would look like.
So just an applied moment on either.
Yeah, applied moment on both sides. Yep, applied moment on both sides. My moment diagram, looks like this. Right, and so if your thing didn't go to the CGC and went like this, your moment diagram would look like something like that, right? And so you do this guy, and you would do a constant moment one, which would shift it up or down. And the way that he does that in his notes down here to shift it up and down, he has a constant eccentricity, right, which gives you a constant internal moment. Yeah. And so just to kind of demonstrate, we just did this one, right? We did it up there by doing the equivalent equivalent deflection. And so if we go like this, just to kind of show that it works. If you didn't trust Stanton, and you go like this, delta 1. When I say delta is equal to 2/3 delta 1. And then you look up delta 1. Right, see it says 2/3 delta 1 is what this one is. Then you calculate delta 1. Here it is right here. Delta 1 is equal to epsilon sub P1 times FP L squared divided by 8EI. If you put that in there and simplify, you get delta equal to 2/3 epsilon sub P1 FP L squared divided by 8EI. And that simplifies down to FP EP L squared all over 12EI. So he was not lying to us. Fancy. Is that what you said, fancy? Yeah. He's English, remember? He's a fancy dude. Speaks with an accent. Okay.
For the grades case, is there any standard equation? Is that always a quadratic, or how do you
Oh, the drake.
assume what the?
I always assume it's quadratic, but I think and I think that's how because this is made by them, right? We put it in there. If you look at, use a big word for it here. If you look at, when it's just draped like this, as it's going across, it's actually not a quadratic. It is funicular, I believe is the word. Doctor, remember I'm a doctor. Funicular shape. You don't buy me on that one.
Well, maybe it's catenary just
Catenary, same deal. Yep. Catenary, funicular. I use them interchangeably in my. It's very subtle, very subtle difference between the two. I kind of want to Google funicular. That's the word that came to mind. But catenary is one that I heard. I don't want to do. I'll do it here. It's like I can lie to you on what I find in my. I don't know how to spell it either, so that's a good thing I'm doing that here. Particular structure is said to be a structure which can achieve equilibrium state by adopting mechanisms of right form shape. A little more, choose a particular shape. Googled it. Particular forms, particular geometry. Cables and chains. I like this one. Described and visualized with cables or chains suspended from 2 points that adjust their form for any load and tension. But funicular structures may also be compressed like arches. Yet, although funicular tension structures adjust their form for pure tension under any load, funicular compressions may be subject to bending and additional compressions. Okay, I like that one. And then catenary is another one. So they're close to each other. They're really close to each other, but they're not exactly the same. And so usually we design them as like being parabolic. That'd be a great question for Kyle, like on what they do when they have that thing going through. Like, what assumed shape do you have?
Equivalent load onto that, like what?
Yeah, just the dead load of itself would take on that cable would take a certain shape. It's close to being quadratic, but it's not. But I think that, and I'm not sure what they do in the real world. If they assume, like the computer program assumes a shape to it, like what shape are they assuming? I'm assuming he's assuming a quadratic in this case. Yep. The math kind of looks that way. Okay. Immediate deflection and cracked beams. Okay. Okay, so we'll kind of lay this thing out. We have time to do this in 6 minutes or so. So all that stuff before is for uncracked, like linear members, right? But if we're being cracked, we're not going to deal with cracked members in here. But it's kind of I would say this, typically not an issue. Right? Because again, the whole reason we're doing pre-stress to begin with is to control cracking, right? So like, why are we going to let this thing crack? Like we calculate deflections under service conditions. Remember, that's a service load condition, right? Because people don't die if you violate these requirements. And so you're not factoring your loads, you're not pretending your loads are bigger than they are, you're not pretending your capacity is smaller, you're just calculating deflection. So if it's a service condition, why are you doing a pre-stress member that's cracking? Because the whole point of the pre-stress is to prevent it from cracking. So I don't think this happens very often. But if it does, how would you deal with it? It's a nonlinear problem. You have nonlinear FEA. You could integrate curvatures along the length using nonlinear moment curvature relationship. Right? With that equation before, you look up the moment, you look up the curvature, and then you go from there. So that's one way of doing it, right? Right? Or there's approximate methods. Right? And in particular, I'm talking about ACIs, I cracking, which is bilinear, or I effective. Right? I think that you said if you've taken regular reinforced concrete, you've dealt with both of these things, right? Regular reinforced concrete, biliad. The hell's that? What was I saying? Bilinear. And that was supposed to be or. Oh yeah, bilinear or I effective. Right? Regular concrete, it crack all the time, right? As soon as you put any load, almost any load on a concrete beam, it's going to get a crack, right? And so that's where these other methods come in, these approximate methods, okay? And they come in regular reinforced concrete all the time. Usually you design just for like H minimum, but if you do sharpen your pencil and calculate deflection of regular reinforced concrete, they also apply here as well. I'm also going to say C, PCI, Chapter 5. example, if you wanted to dive in a little bit more, they go through an example of calculating deflections of a cracked member. But it's all based on, back to our moment curvature relationship. Good thing we talked about moment curvature relationships. Now you know what it is. You got moment over here, and curvature over here. And what it assumes, one method assumes bilinear. So down here, it assumes a slope of your moment curvature to be EIG, my gross moment. And then after it hits MCR, this would be MCR, then the slope of this becomes EICR. Right, so you calculate your deflection. So you calculate your deflections before it cracks. This is why it's bilinear. You calculate the deflection before it cracks. That's before you get to the moment of MCR. And then you calculate your deflections with the load that's after end cracking using a different EI. The EI obviously is going to be lesser up there, right? And so what ACI gives you is an equation for ICR. ACI provides and for ICR. That's what they give you. Okay. And we kind of mentioned this last time. The IG, or the I effective, they do is they kind of cut the corner. It's just a single method. Right? The other method is they just assume that it cuts that corner. And this would be EI effective. And then ACI also gives you this. Right? It's all very empirically based. Right? They just ran a bunch of tests. This isn't right, by the way. I mean, like, so what it does, if you think about a simply supported beam, you got to go here in a second, or I got to go, we both got to go, we all got to go. But if you think about like calculating the deflection like this, right? The moment diagram, obviously, it's going to go like this, right? It's maximum near the middle, but then not as much. This assumes the whole beam is cracked. The whole beam has a crack, right? Only in here is, someplace across the middle it's cracked. And so if it's only cracked in the middle, then how the hell, like, this sounds really great, like, oh, having just two methods and having the ICRs and the IGs. Well, near the ends it hasn't cracked, and it's contributing to the deflections, but it just assumes the same EI across the whole length and stuff, and it gets weird. But it's just an approximation. It's empirically based. They did a whole bunch of tests, and they said this works really well. That's one way to do it. And the code, or the ACI, kind of goes through and walks you through how to calculate those deflections. I don't think we're going to do that in here. We're just going to show you that you may be called upon it to do it in the future. Probably not going to be an issue, but if it does, this is how you do it. Okay. Next, we're going to talk about long-term deflections. So all this stuff we talked about so far is immediate. What happens immediately when you apply the loads? What are those effects? But what happens over time? Creep and shrinkage and pre-stress losses and all that change those deflections. How do we account for that? And that's kind of the next step. It turns out we just guess in that as well.